Hi there. Can you solve this? Well, neither can I. But Wolfram Alpha can. So this is the thing that probably I have most to thank for passing university, especially the math classes in it. If you don't know Wolfram Alpha, it is a engine. It's from the creators of Mathematica, but it is online. And it can do symbolic math. So it can integrate this expression, for example, and you'll get the solution here. And if you have the pro version, it can even give you a step-by-step solution of how to get there. So this part of math is an entirely different part than we usually do with computers. Usually we do numeric math, working with actual values. But here, it's about symbolic math. It's about manipulating expression, in this case, integrating them. So, here is a paper by Facebook AI Research called Deep Learning for Symbolic Mathematics by Guillaume Lample and François Charton. These people have basically tackled the task of doing these mathematical reasoning, solving these mathematical problems in a symbolic way using neural networks. So they start out by saying here, neural networks have a reputation for being better at solving statistical or approximate problems, that's what I meant by numeric, than at performing calculations or working with symbolic data. And in this case, they go about this other than other people have. So let's look at how they did it. We can express symbolic mathematics in these kind of trees, right? So an expression like these up here would be expressed into this tree. So you would have a plus this through 2 plus 3. Of course, there's an implicit bracket here. So you'd have this plus right here, the 2 here, and the entire right-hand side here. So you can basically decompose it into trees like this, or this, or this. Here you also can have the differentiation operator as a symbol in there, just like any other operator. Moreover, you can basically decompose everything they have here into binary and unary nodes in a tree. What that means is either, like a plus sign, it has 2 components, so a left and a right hand side that should be added together, or like the cosine, it has 1 argument, namely the thing that it should take the cosine of, right? So a lot of people have tried going about this problem by working with these trees and basically training neural networks to... So first they use kind of a parser to decompose such a thing into a tree like this, and then use neural networks, let's say tree recursive neural networks or so on, to kind of make sense of the tree and solve it in a recursive manner or something like this. But that has its limitations. So what these people from Facebook AI did is they viewed it as a natural language expression problem, right? So they say, no, let's actually go with trees as sequences, right? So you can see that this mathematical expression, for example, is already a sequence, right? It's simply a sequence of tokens. But there are many different ways of expressing this. So you can say 2 plus 3 times the parentheses. You can say 3 times the parentheses plus 2. You can, turn many things around, and there's always these parentheses make it harder, and so on. So what they do is they say, okay, let's actually go from this thing to a tree. So let's go up to this tree representation, and then let's take the tree representation, because the tree representation can be normalized, and then let's put that again into a sequence representation, such as this one. And this is called reverse Polish notation. And it has multiple advantages over the old expression. So let's keep that on the right-hand side here. This is the same thing, except it's what is called a prefix notation, whereas the thing on the right here is called an infix notation. infix because the operators, such as the plus, is always between its arguments, right? So it's left-hand argument and its right-hand argument. In prefix notation, the operator is always in front of its arguments. So this operator here has as a first argument this, and as a second argument this, right? Now the cool thing is, if you express a tree like this, you can simply go and use a stack machine to solve it. So you can basically go, I would say you can go from the right here and just use like a 2 and a 5 plus, and let's do it by hand actually. This is fun. So we have plus 2 times 3. If you're a boomer like me, you remember you had to use calculators like this and you couldn't use the infix notation. So you go from the right, you say 2, 5 plus. Cool, that's 7. So scratch that, put 7 here, right? So your new stack is 3, 2 times this, right? Then you go again from the right and you go 7, 3 times. Okay, that's 21. Cool. 21. Scratch this. Now it's 21. 2 plus 21 is 23. I'm fairly sure that's the solution. Well, correct me if I'm wrong. But this is how you would go about solving like this. So it is the same expression as the original one, but it doesn't use any parentheses, and it is derived from the tree basically. So it is you can normalize it much more in order to find unique expressions. So what this system does is it transforms any expression into a prefix notation, such as this one. Oopsie. And then it uses a sequence to sequence model in order to derive the solution. Now, just how crazy is this, right? So we go from this thing here, right? From this thing, and the solution is 21, right? And the neural network is simply trained to do sequence to sequence from this to that, right? Sequence to sequence. That means it basically parses this as on a token level, right? And then it outputs these tokens without. So during training, you simply give it the input here, and you give it the output, and it's supposed to learn how to transform one into the other without you giving it any sort of mathematical ability, right? Without you telling it what does a plus sign mean, without you telling it this algorithm that I just told you. Now, this by itself is already pretty astounding that you would try such a thing. It really transforms the string, so this, not the mathematical equation, but the string of this into the string of that. Now, they don't do it on numbers. Like, I don't think that would work as well if you were to make it kind of calculate numerical things like this. As we said, this is symbolic. So what it can do is it can, for example, integrate. So if you have an expression like let's see some on the bottom here. So if you had an expression such as a polynomial, here, an expression like this, right? You would like to find its integral. That is a problem. That's one of the problems we had at the beginning, right? This integral right here. You can write this in a string, like we said, and then derive its solution right here, and have the neural network learn to map one to the other, right? To map this to that. So the way it goes is it would map this into its tree representation. It would map this into its prefix notation, right? it would also map this to, sorry, let's take another color here. It will map this into its tree. Then it will map this into its prefix notation. And then that's the training data. The training data is take this, derive that, right? And at inference time, of course, you won't have this here. You'll simply be asked to output a sequence as a normal natural language. Like you can think of machine translation, right? This thing translates problems into solutions. It's crazy. I mean, it's not technically super challenging, but it's crazy that it works, or that it could work, right? So we'll see how this actually works. They use a transformer model, which is a classic model. If you don't know what a transformer is, I have a video called "Attention is All You Need" about transformers. You can basically use them to do these kinds of tasks, to map one string into another string. So yeah, so they go into detail here of how they construct the data set and how big the problem space is and so on. Ultimately, they compare their system to Mathematica, I think, and Maple and Matlab, which do the same thing. So Mathematica, which is the kind of desktop version of Wolfram Alpha that I've shown you, you have it here. So integration is the task of integrating, let's say, these symbolic expressions. ODE order 1 and order 2 are slightly different tasks where you're asked to solve an ordinary differential equation, which is also a task in symbolic mathematics. If you compare it to Mathematica here, and they give it Mathematica a limit of 30 seconds, what Mathematica will do is it will kind of search the manipulations that it knows, right? So the advantage of this is it can always give you, let's say, a step-by-step solution if it finds a solution, right? It will just start and it will do a tree search manipulating the expression you give in until it reaches a satisfactory solution. But then once it has that, it can give you a path through the tree which leads to the solution, which will give you a step-by-step solution so you can understand it. The system that Facebook designs here doesn't do that. It simply takes, right? It simply takes the input tokens, like this is the input, and it just gives you an output. That is learned, so that the network per se doesn't understand math. It simply learns from many, many examples that to transform, to come up with good hypotheses. So if you compare here Mathematica, for example, it can integrate 84% of the things that they put into it. It's not said whether it gets it wrong or simply times out in the rest. I would say it times out because probably Mathematica never gets it wrong because it's an actual symbolic manipulator with defined rules. So I guess the rest 16%, it simply times out, doesn't find a solution. Whereas this Facebook system, and they say usually finds the solution in less than a second, finds these solutions in 98.4% of the time with a beam size of 1. Now what does the beam size mean? At decoding time, if you have a seek-to-seek model, you can always opt to do what's called beam search. So when you have a input sequence, let's actually give an example. A cat jumps, right? And you generate an output sequence. Let's say the task is simply to continue the sentence, right? To continue the sentence. So you can generate an output sequence. The output sequence could be over the dog. What you can do is this is beam size, would be called beam size 1 or no beam search at all. You can do what's called a beam search in that each step you actually generate multiple hypotheses and then keep the best ones in memory. So in a beam size of 10, you would always consider the 10 most probable solutions, and you would kind of evaluate all 10 and then always keep the 10 best. Let's see how this goes. Let's do a beam size of 3 in our case. So a cat jumps, and then you could come up with 3 different things. This sentence could continue. Cat jumps over, a cat jumps between, and a cat jumps swiftly. Right? So these are your 3 hypotheses. Then we go to the next step. We have to evaluate each of them. So a cat jumps over the, over a, over me. A cat jumps between the, between 2, and a cat jumps between many. The cat jumps swiftly, end of sentence. Cat jumps swiftly over. Cat jumps swiftly and. Right, these are all valid continues. So of these 9, you would now select again the 3 that overall have the highest likelihood. Maybe that's the following. A cat jumps over the, a cat jumps over a, and a cat jumps between 2. These 3, right? So you just keep these 3, and then in the next step, you again from these 3, you would want for each 3 hypotheses and so on. So this is what's called a beam search, and if you give it a beam size of 10 or 50, this system tends to improve even more. The way this system works is quite different from Mathematica, in that Mathematica, as I said, is a symbolic solver that never makes mistakes, but can't fail to give you a solution. This system simply generates an output sequence that is not guaranteed to be actually a solution to the problem. It's just a hypothesis. But then you can quickly check whether the hypothesis is correct. So the nature of these math problems. With integration, you can simply differentiate. And with ODE, you can simply plug them in to see if they're a solution. It's kind of like your classic, let's say, NP-hard problems, or like a SAT solving, where you can quickly check whether something is a solution. So if you have a system that generates you 50 hypotheses, you could quickly check which one is actually correct. So these numbers here mean that one of these 50 that the system came up with was a correct solution. And if you allow for such many hypotheses, you can see it goes up quite a bit. For example, the ODE solving is almost the same, and here it's even worse if you take ODEs of order 2. It's even worse than Mathematica, but if you allow for larger beam sizes, you see it dramatically goes up. And so it's a different approach. I wouldn't be surprised if Mathematica would actually implement something like this very soon, or just buy this off of Facebook or something, or Facebook buy Mathematica. In whatever way, this clearly is a different approach, and it appears to work better. But there's a caveat. So here's the caveat that I see with this kind of thing. These evaluations are done on datasets, of course. And this paper goes into big detail on how to generate these datasets, right? So they have to, pay attention to many things, like many solutions are equivalent. For example, here, that this solution and this solution to this equation, to this differential equation, are the same. So they, have to use a symbolic framework to check whether the solutions are the same and so on. It is very good work, but they do evaluate on expressions that fit into their data set. So here in their data set, they say, okay, we evaluate, expressions with up to 15 internal nodes, 11 leaf values for these 4 binary operators, then these 15 unary operators. So the expressions that they train on fall into this data set, right? also just numbers from -5 to 5. So it is kind of to be expected that a system that is trained on these things would perform very well on these things, as opposed to Mathematica, that is, a general purpose tool. Moreover, if you look at sorry, I think this is further down. For example, in integration, for the integration task, they have 3 different ways of solving, of generating data. They have the forward way, where they simply use a symbolic integrator to generate expressions. They have the backward way, where they start from the integral and then differentiate it in order to obtain a training pair. And they have an integration by parts method. So these are 3 different methods to come up with problems for this system to be trained on. And they have very different properties, to the effect that if you train with one, just one, it won't work well on the other. So if you train with the forward method, it will work very well on data that has been generated with the forward method. So this is down here, this is what it's trained on, and this is what it's evaluated on, right? You can see the diagonal is very, very strong. But if you train with the backward method, but you evaluate on data generated with the forward method, it is actually very poor. That's because in one case, generally the solutions are longer than the input, and the other case, the solutions are shorter. So not only does this system only work on the particular task here, it is actually very attuned to the way that this data was generated, right? So in fact, I would postulate that this training data is only probably a very small subset of all of the things that we would like to integrate. And again, the problem is made kind of worse because their evaluation set would also come from their distribution. So what they've ultimately shown is that they can do this on a very skewed, probably very biased subset of this mathematical problem, and on that biased subset they can outperform something like Mathematica, right? They kind of defeat themselves. Yeah, if you look here, even the different integration data generating methods, if you only train on one of them, it doesn't generalize. If you only train on forward data, then if you evaluate on backward generated data, it doesn't work. So even the integrator can't really generalize, so they have to kind of combine different method. And even now, we can probably easily find examples that this integrator can't solve. So, I mean, there is a lot of cool things here, and they show a number of properties that the model learns just from without them telling it to. And it's cool that it works anyway. As I said, this model has no programmed in notion of how math works. But also it kind of shows the problems if you do this via a training data set, in that if your training data set is very skewed and then your evaluation set follows the same generation process, the claims you can make at the end are limited. And to be fair, I don't know what claims they made in the press generally. So I think it's a pretty cool work. Check it out. And that was it. Thanks.